Mean value theorem. Our objective is to use the mean value theorem to prove the existence of a location on a function where the instantaneous rate of change equals the average rate of change. Mean value theorem. Let f be a function defined on a closed interval from a to b. If f is continuous on the closed interval from a to b, and f is differentiable on the open interval from a to b, then there exists at least one number c in the interval a to b where f prime of c, the derivative, equals the average rate of change, f of b minus f of a over b minus a. Meaning, for at least one location on the graph, the tangent line is parallel to the secant line containing the endpoints of the interval. Also that the instantaneous rate of change equals the average rate of change. Now let's pause for a second and take a look at how this works. We're going to draw a function that satisfies Rolle's theorem. So remember, Rolle's theorem must be continuous, differentiable, and start and stop at the same y values. For example, this would satisfy Rolle's theorem. Continuous, smooth, so differentiable with no vertical tangents, and it starts and stops at the same y value. So let's connect the endpoints with a line. What is the slope of that line? Well, the slope of that line is 0 because that's a horizontal line. The slope is 0. Now, let's draw a function that satisfies only the first two parts of the criteria of Rolle's theorem. So continuous and differentiable, but the endpoints are not located at the same y values. So I can start at some y value, smooth and curvy, and end at some other y value. Let's connect the endpoints with a line and estimate the slope of that line. So I'll connect from endpoint to endpoint, and we probably don't need to estimate, but we can actually count it, the rise over the run, down 2 and over 1, 2, 3, 4. So the slope of this line is negative 1/2. 2 over 4 simplifies to 1/2. Is there anywhere else on the function where we can draw a tangent line that has that same slope? Well, there sure is. This and here approximately looks like I can draw a tangent line that has a slope of down 1 and over 2. So the slope here is negative 1/2. This is what the mean value theorem says, that when I connect the endpoints of that continuous and differentiable function, that line will be parallel to a tangent line that is somewhere between those two endpoints at least one place. Essentially, that's what Rolle's theorem does too. Rolle's theorem says that for a continuous and differentiable function, there will be at least one place where the tangent line is horizontal and has a slope of 0. That is also parallel to the line connecting the endpoints. Mean value theorem is less restrictive because the endpoints don't have to be at the same y values, but it's basically saying the same thing. We connect the endpoints, the slope of that secant line will be the same as the slope of some tangent line found between those endpoints. Remember that the derivative means the slope of the tangent line, and the average rate of change means the slope of the secant line connecting the endpoints. The instantaneous rate of change, that is our derivative, and the average rate of change, that is our change in y over change in x over an interval. Slope at one point, tangent line, versus slope over an interval, secant line, and those slopes are the same. It's important to understand this mean value theorem graphically, or we might say geometrically, as we would look at the picture, as well as analytically, where we say the derivative equals the change in y over the change in x. Let's look at some examples. 1. Verify that the function satisfies the conditions of the mean value theorem on the indicated interval. Then, find the number c guaranteed by the theorem. Interpret the numbers c geometrically. So to verify that the function satisfies the conditions of the mean value theorem, we have to know if this function is differentiable and continuous. Well, I see f of x is a polynomial function. So since f of x is a polynomial function, since f is a polynomial, it is continuous on, and we must make it as the closed interval. Of course, it's continuous everywhere. Therefore, it has to be continuous on the closed interval from 1 to 3, and it is differentiable on the open interval from 1 to 3 because we don't take derivatives at endpoints. So here we've verified that the function satisfies the conditions of the mean value theorem on the indicated interval. Now we can find the number c guaranteed by the theorem. Let's practice stating what these conditions guarantee. We'll say, therefore, mean value theorem guarantees that f prime of c equals f of b minus f of a over b minus a for some c on the interval 1 to 3. Now, let's plug in the a and the b that were given in our interval. Also take the derivative of our function. F prime, looking at our function f of x, is 3x squared minus 7 equals f of b minus f of a. So that's f of 3 minus f of 1 over 3 minus 1. So we've got 3x squared minus 7. F of 3, plugging 3 into our original function, gives us 12. F of 1, plugging 1 into our original function, gives us 0. And 3 minus 1 is 2. So we get 3x squared minus 7 equals 6. 3x squared equals 13. X squared equals 13 thirds. So x equals plus or minus the square root of 13 thirds. Now, mean value theorem guarantees at least one place. There could be more than one. There could be two. However, notice our interval, there is only one. So the c value that we're finding here is just the positive square root of 13 thirds, and that's the only one. Now, let's interpret the number c that we found geometrically, meaning what does it mean about the graph? So looking back at some meanings of mean value theorem, the tangent line is parallel to the secant line containing the endpoints of the interval. Let's be specific about this for our function. So we can say at the x value, square root of 13 thirds, the slope of the tangent line to f of x is the same as the slope of the secant line connecting what points? Well, the x value 1 gave us the y value 0, so 1, 0. And the x value 3 gave us the y value 12. Another way to say this is the tangent line at square root of 13/3 and the secant line connecting those 2 points are parallel. Two stationary patrol cars equipped with radar are 4 miles apart on a highway. As a car passes the first patrol car, its speed is clocked at 55 miles per hour. 3 minutes later, when the car passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the car must have exceeded the speed limit of 55 miles per hour at some time during the 3 minutes. Now, it looks like from what it was clocked that this car did not exceed the speed. So let's use the mean value theorem to help us prove that it did have a speed higher than 55 miles per hour at some time during those 3 minutes. So we must make sure that we're working with a continuous and differentiable function. So let's talk about the function that we're talking about is the position of the car. So we can say since the position of a car is continuous and differentiable, of course everywhere, because we can't skip any moments in time, we can apply the mean value theorem. Remember, the mean value theorem says the instantaneous velocity, meaning the speed at one point, at least for this situation, it's the speed of the car, since the car is only going in that one direction, will equal the average velocity, or in this case, the average speed. So let's find that average velocity or the average speed. So thinking about what that is, we're thinking miles per hour. So we want to find the change in miles. They said 4 miles apart over the change in hours. And this was over a course of 3 minutes. Now, these are not hours, and we are finding the speed in miles per hour. So we need to convert this. 3 minutes times 1 hour for every 60 minutes. That way our minutes cancel out and leave us with hours. And that gives us 4 divided by 1/20th, since 3 divided by 60 makes 1 over 20, which is 4 times 20, or 80. Wow, that car's average speed was 80 miles per hour. So according to mean value theorem, it must have exceeded that speed limit of 55 miles per hour since its average speed was 80 miles per hour. Three, let f be a function that is differentiable on the interval from 1 to 10. Now note, when they say differentiable, we are able to conclude, so I'll say therefore, that the function is also continuous on that same interval. Now we don't know that it's continuous on the closed interval from 1 to 10. Let's keep reading. If f of 2 equals -5, and f of 5 equals 5, and f of 9 equals -5, which of the following must be true? 1. The graph of f has at least 2 zeros. Zeros means f of x equals 0. The function hits 0 somewhere along the way. Notice that we're starting at x equals 2 and ending at x equals 9. So we're really only looking from 2 to 9. and that is an interval between 1 to 10. So concluding from this, we can say that the function is continuous on the closed interval 2 to 9, and therefore differentiable. Well, because it's differentiable everywhere, it's going to be differentiable on a subinterval of 1 to 10, which is also 2 to 9. Now we want to prove that the function value hits 0 somewhere, at least 2 places. That doesn't include any derivatives, so that's going to be our intermediate value theorem, which says that we want to hit an intermediate value. Now notice we go from -5 to +5 on the interval, and then back down to -5. So of course, if we have a continuous function, we've got to hit 0 along the way. So IVT tells us that if 0 is between two of these endpoints, such as f of 2 and f of 5, then we have to hit 0. Also, it's going to hit it again going from +5 back down to -5. So again, 0 is between 2 points in that interval, f of 5 and f of 9. So therefore, this one must be true. We're going to hit 0 twice in this function because of IVT. So we'll circle that one. Let's see what's next. 2. The graph of f has at least one horizontal tangent. Horizontal tangent means the derivative equals 0 somewhere. Well, that is Rolle's theorem. So let's ask ourselves if Rolle's theorem applies here. So remember Rolle's theorem, we need a continuous and differentiable function. We have that. Also, we need to know that the endpoints of the interval have the same y value. So I see a y value of -5 and another y value of -5. So because f of 2 equals f of 9, Rolle's theorem is satisfied and guarantees at least one horizontal tangent along the interval. So we'll also circle this one. 3. For some c between 2 and 5, f of c equals 3. Again, that's not a derivative, so that one is also indicating intermediate value theorem. So between 2 and 5, what do we have? F of 2 is -5, f of 5 is +5. Is 3 between those values? Yes, it is. We have a continuous function, and 3 is between f of 2 and f of 5, so 3 must be hit. True. Finally, for some c between 2 and 5, the derivative equals 10/3. This one is not the derivative equals 0, therefore we'll be using the mean value theorem. The mean value theorem needs the function to be continuous and differentiable, and it is, so mean value theorem applies. So how about the average rate of change from 2 to 5? Looking at those right there, we're going to do f of 5 minus f of 2 over 5 minus 2. F of 5 is 5, f of 2 is -5. So that makes 5 minus -5 over 5 minus 2. 5 minus -5 is 5 plus 5, which is 10, over 3. The derivative must equal the average rate of change according to mean value theorem at least once. So this one is also true, and it looks like they are all true. Thanks for watching.